Self-test problem number 2.
Yeah.
Chapter 7. An urn has N white balls and M black balls that are removed one at a time in a randomly chosen order. Okay. Find the expected number of instances in which a white ball is immediately followed by a black one. Okay. All right. Well, let's see. This is probably one of those instances where it's going to be best or easiest, at least, to try to write this thing as a sum of variables of some kind. So have you thought of like a variable that might actually be helpful?
Yeah, so I was letting the indicator variable be if the basically be 1 if it's like x sub I is equal to 1 if a white black sequence starts at
Position I.
position I, yeah.
Yeah. Yeah, that's what I was thinking. All right. So let's see. Let me get this thing out here. Okay. Let's see. So you said, so what do I have? M or N white and M black. And apparently you just keep going. This one, are you just going to go all the way till they're all gone or something?
I assumed so, yeah.
Yeah, that's right. So remove one at a time until gone. Okay. So what? So you're going to let X I equal to the event where you have like what, a white black starting at position I.
Yeah.
Okay, and what's the deal? I guess 1 is going to be less than or equal to I is less than or equal to N plus M minus 1.
Yeah.
Okay. So X, which we want to be the number of, is it white black? Is that what they said? Which a white ball is immediately followed by a black one. Number of white black subsequences That's just going to be x1 plus x2 plus dot 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 plus x sub n plus m minus 1. So that's basically how you set this thing up.
Yeah.
And I assume you just said, well, okay, I want the expected value of x, right?
Yeah.
And I mean, one thing that's a little bit troubling, at least at first, is that you realize there's a high degree of dependency between these. You understand?
Yeah.
So like x1 equaling, you know, hang on. So xi is equal to the indicator of that event. Does that make sense?
Yeah.
I wrote x. That doesn't even make sense what I wrote. Xi equals wb starting at position I. That's not even like a number. It's just a concept. You understand? So so xi. So let me see. Xi is equal to the indicator of this event. The indicator of this event. Does that make sense?
Yeah.
It's 1 if that happens, and if 0, it's 0 otherwise. So at first, it's kind of troubling when you have these sums of highly dependent random variables. But when you do the expectation, the expectation of the sum is the sum of the expectations anyways. Does that make sense?
Yeah.
Actually, all of these xi's on their own are distributed to any other xi. Yeah. So xi like has the same distribution. X1 has the same distribution as x2. X2 has the same distribution as any of these things. Okay. So wouldn't it just be n plus m minus 1 times the expected value of the first thing? So you add all these things together, and all of them are equidistributed. But what's the expected value of x1? Wasn't that just the probability of, WB at position 1 and 2? Yeah.
Yeah.
And what's that probability?
That would be n over n plus m times n plus m over n plus m minus 1. Or sorry, m over that.
Okay. So it's a sum of two things. One where you had, oh, wait. Say again. Sorry.
So you'd have n over n plus m, because you have to choose a white ball, and then times m over n plus m minus 1.
Oh, I see. Yeah. So you choose a white ball. Oh, well, I was going to do it this way. So I was going to do in choose 1. Right. Okay, well, you're saying the same thing. M choose 1. Okay. And then basically the rest of the things are just in a random order, right? So wouldn't it just be n plus m minus 2 factorial divided by the total number of sequences of white and black balls, which is going to be n plus m factorial. Is that exactly what you just said?
I think so.
Because almost everything cancels, yes?
Yeah.
So it's just going to be nm, n times m over n plus m, n plus m times n plus m minus 1. And the n plus m minus 1 is just like cancel. And you get nm over n plus m. Is that not the answer they have, Matthew?
That's the answer they have. I think what I'm having trouble with is how they just go from the sum of all the expectations to just considering one of them.
Right. And the reason you can do that is because you realize if you just focus on any one of these, if I just focus on any one of these, for instance, like X5, okay, and I'm just concentrating on X5, then I'm only looking at position 5 and position 6. And the other ones are just running wild. Does that make sense?
Yeah.
So, but that's no different from concentrating on position 1 and 2. Do you see?
You can just ignore all the
Yeah.
other stuff.
Right. And I mean, in particular, like if you did X5, would the computation, if I did the expectation of X5, would the computation have been any different? I mean, think about what we just did when we computed this thing. Like if we're just if we're
No.
looking at the expectation of X5, would it be different?
No.
No, all you would do is you would say N choices for the white, M choices for the black in positions 5 and 6, and then just put any random, sequence of the other N plus M minus 2 balls in the other slots, and then divide by N plus M factorial. So you would end up with the exact same result. Does that make sense?
Okay.
And that makes sense when you just think about kind of sliding those two positions around. It's like, well, this doesn't really matter what two positions I'm concentrating on. So yeah. Make sense?
Yeah.
Cool. So are you just kind of going through these self-test problems on your own?
Yeah.
Yeah. This stuff with indicators is highly powerful. I mean, you can do some really complicated problems, and I'll do some that are fairly complicated, as long as you're willing to write things as sums of indicators. And it turns out that's an important skill to have, because the central limit theorem, which is probably the last thing we'll cover, requires that you have a sum of random variables. And you might say to yourself, well, how in the world can I think of the binomial random variable as a sum of things? Well, that's what we did in the example in the lecture for today. It's a sum of indicators. And it turns out that as long as you can write a random variable as a sum of, like n things, the central limit theorem is going to apply, and you can say some really powerful things. So, yeah.
Okay.
Well, do you mind if I take a question from Logan here, Matthew?
No, that's all I had. So.
Oh, okay. Cool.
Yeah.
Well, thanks for asking.
Thank you.